Okay, well, let's go ahead and get started. I want to welcome everybody to our next edition of Data Club. This is our first one in the new year. My name is Eric Olson. I'm on the core OS, or basically the developer platform team within Cosign, which is part of Azure. And if you haven't been to Data Club before, just a reminder what we're here for. Basically, these are training and sharing sessions for data. I say data science topic. It also includes data engineering related work. And there's a number of different formats we use, which you've probably seen before if you've been here before. But this is our place for collaborative learning, our chance to share with each other and actually learn from what other people are doing and the types of problems they're working on. These are basically training sessions or information sharing sessions to help grow the capability of the organization, or a lot of times just make people aware of what's out there if you're not aware. And it also builds you opportunity to build connections with others in the data community who might be working on similar problems, who find help, essentially. So it's a networking opportunity. And so our first rule about Data Club is to talk about Data Club, as to participate and learn together. That's how we leverage our learning to get better. And then if you see something you like here, be sure to share it with those that couldn't attend, or remind them there's a recording. They can get it afterwards and they can check it out. And then finally, looking ahead, we have these sessions about every 2 weeks. So our next session is on February 7th. Or tentatively right now, we're going to be talking about Azure Ignite impacts, so some of the data analysis around Ignite. And then on the 21st, we'll be revisiting the business intelligence graph, better known as BIG, to get some updates of what's going on there. So we're in our commercial space. If you want to keep up with information about these sessions, you can join the Data Club alias on ID Web. You'll get all the announcements and all the meeting requests. And then if you miss anything here today, what I'm talking about, then don't worry. You can always go to aka.ms/dataclub and you can get all the links for the slides, the talks, and the videos. And then finally, after the session, I will send out a very short survey because we are data folks. We want to know what you think. So we have a feedback survey. It takes maybe 5 minutes to fill out. So you can give us feedback on what you like, what you didn't like, what you'd like to see, things like that. And with that, I will now turn it on to David to talk about Neo4j.
Hi, everybody. Thanks for taking the time today. I love talking about graphs. Let's do some of that. Today, we're going to talk about introduction to Neo4j and graph databases. Since this is a data science group, I do want to, towards the end, get to talk about graph algorithms and some of the data science applications. But because graphs represent such a different way of thinking about data, we need to go through some basics first. This is who I am. I'm a partner solution architect at Neo4j. I have a pretty fun job there because about 50% of it is business and about 50% of it is technical. I do a lot of integrations between Neo4j and some of our strategic partners, Microsoft and Azure being one of those. But I get to play a lot, and I get to play with a lot of new fun stuff from all over the industry, and that makes me happy. You can get me on Twitter. Send me an email if you have any question after this session. A couple of things that I want to cover in this session. Go over an introduction into graphs and Neo4j and what the relationship between is. Talk a little bit about why people are using graphs and when you would use graphs versus some of the alternatives that you have. We're going to talk about the underlying property graph data model because you can't really do rigorous analysis or data science unless you understand what's underneath. We'll talk about the Cypher query language and about how we query and manipulate graphs. Talk about some data import and then how we develop applications. We're going to have some demos in here too, so as we go, we will have one demo from Ambrose that's about Microsoft-specific stuff, and then I'll show you some other demos to give you a kind of a flavor of the tool set around this. We'll also talk about graph algorithms and data science applications. So if you are one of those technologists who doesn't want to just listen to slides and high-level theoretical stuff, take note of this. If you want to follow along and actually use the software while we're talking, try out things that I'm talking about on the slides, this is how you do it. We are in the Azure Marketplace, so you can search for Neo4j Enterprise and launch a single instance. Version 3.5.1 is the latest that's on the Azure catalog. Or if you know absolutely nothing about Neo4j and this is your very first experience, go to neo4jsandbox.com. It will allow you to launch any of the sandboxes that you see on the right-hand side and get you to a GUI really quickly so you don't have to think about, what port do I go to, any of that stuff. Sandbox is the fastest way, but there is the Azure way too. On Sandbox, you're going to get a free temporary instance that only lasts for about 2 days, I think. and it starts preloaded with data, so you don't need to know how to load or query or do really anything with an empty database. So with that out of the way, let's start talking a little bit about graphs and the basics. So why graphs? Ankit was saying at the beginning of the session, he got this sticker at our conference, Graph Connect. Graphs are everywhere. We truly do see that. Basically, the entire world is a graph and everything is connected. You have people, places, and events that are thoroughly connected with one another. Companies and markets, countries, history, politics, there's so many endless examples of these things. It's very natural and visual for human beings to connect things in their mind as graphs rather than to use some of the other formalisms that we've become accustomed to as computer scientists and as technologists. We learn how to think about things in terms of relations and sets and JSON documents and things like that, but that's an abstraction that we've mapped a more reasonable understanding onto, not how our brains work. Our brains tend to think of these things as connected nodes and edges, whether it is flights going all over the globe or any other use cases. So before we get into the bits about Neo4j, let's talk a little bit about the business side of what people are using Neo4j and graphs for. Our business is primarily focused on the Global 1000. We have a heavy presence in retail, finance, and a number of other sectors. To give you three concrete examples of how we're transforming large enterprises, we do real-time promotion recommendations for a lot of these big retailers. And so, whenever you see that somebody has had these record Cyber Monday sales, part of that is, consumers buying more online, and part of it is that the retailers are consistently getting smarter about how to do product recommendations. A lot of that product recommendation stuff is driven by Neo4j behind the scenes, in that we can model the products and who is buying what as a graph, and then we can create social recommendations for users. You might like what your friends have purchased, and any number of other recommendation approaches using Neo4j. Marriott uses us for real-time pricing with 300 million pricing operations per day. One of the other things that Marriott has found, and we can talk about this a little bit more in the architecture parts, but we tend to require a whole lot less hardware. And when we get to index-free adjacency and talk about how the database works a little bit, you'll understand why that is. Folks are frequently finding that they can replace large fleets of relational database clusters with fewer instances of a Neo4j graph database when they're really focused on real-time relationships. And we also work with large postal services for handling package routing in real time. And so if you think of the traveling salesman problem or a network of roads as being a graph of sorts, package routing is full of shortest path type queries. I need to get a package from point A to point B going through the fewest number of logistics hops in the middle. So that's what you would think of as a fundamentally graphy problem. Just to kind of go through a number of other use cases we cover. In two categories, internal applications, we have a lot of folks using us for master data management, and so they would take the metadata from all of their systems and then put it into Neo4j and draw a lot of correspondences back and forth to say this field in this system is equal to this field in this other system, a metadata catalog, if you will. We get used for network and IT operations, where you have to understand the topology of a network and how all of your infrastructure relates. And this is used for things like critical path analysis. So which router, if I knocked it down, would knock the whole data center offline? That's an example of another kind of a graphy use case. And fraud detection. So a lot of our financial clients will put transaction data into the graph, and then we'll ask, maybe I sent 5,000 here, 5,000 there, 5,000 to a third location, but if all three of those recipients of the funds are controlled by the same party, in aggregate I've transferred 15,000 to somebody. And so it gets used to sniff out financial fraud. In customer-facing applications, real-time recommendations, particularly products for retailers, graph-based search, and identity and access management. So that's what graphs get used for. What are they? In much the same way as a relational database has a set of tables, rows, columns, and schema, let's talk a little bit about how graphs are structured. Fundamentally, it boils down to nodes, relationships, properties, and labels, which we'll go through. A node is simply an object in the graph, and it can be labeled. A label is like a semantic category, much as you might have an entity in an entity relationship diagram. So in this particular graph, we've got persons and we've got a car. Relationships relate nodes by type and direction. Relationships in Neo4j are always directed. You may traverse them undirected if you want, but they always fundamentally have a direction. So a relationship always has a type. So if you are traversing a relationship, you can segment that out and say that you only want to traverse certain kinds of relationships, not just any way that these two nodes are connected. So in this particular case, we can tell from this really simple graph that these two people love each other, they live with one another, one owns the car, but the other drives it regularly. So properties are basically key value maps that get associated with nodes and relationships. They can go on either. And so by adding properties on top of these nodes, we realize that it's Dan and Ann who love each other and that live with one another. Dan has a Twitter handle, and when we look at this relationship drives, Dan drives the car, we can put metadata on the relationship and assert that that's only been since 2011. So basically, you can think of a node and a relationship as a property container, where properties are simple key value maps.
Can I ask a quick question?
Yes, sir.
By relationships, it's the same as edges, right? That's what you mean.
Yes. So in the graph world, sometimes people refer to vertexes and edges. We tend to talk about nodes and relationships because we find that language is more accessible. But in the math literature, you'll see vertexes and edges, and we're talking about the same thing.
Another
Yes.
question. So for the relationships, so there are two persons, right? So are the relationships only between nodes, or you have some sort of like ontology on top of like person, and then the relationship is between person as an entity and the car as an entity?
Okay. So there's a couple of different ways of going with that question. There is not the question for those who didn't hear it is there some sort of an ontology on the top that specifies what kind of relationships you can have? We're going to talk about constraints. You can assert constraints that certain kinds of nodes must have certain kinds of relationships. However, those constraints are optional. Neo4j does not have an ontology layered on top of it. And those sorts of schema constraints are optional, right? So, and furthermore, the constraint may assert that you have to have a relationship, but you cannot, for example, assert that there could never be a drives relationship between two persons. Okay, that would be a different sort of constraint. Does that answer your question for now? We're going to be talking more about constraints. Any other questions before we go on? Okay. So just quickly, summary here. Nodes are entities with complex value types. Relationships connect them and structure the domain. Properties are basically these key value pairs. They tend to express metadata about your nodes and your logical entities in your domain. And labels group nodes by role. And so usually you think of labels as the entities in an ERD. Nodes you would think of as the instances, the rows in a table. And relationships can be thought of as joins, which we'll go into much more depth on that. Yes?
Labels different from properties. It seems like this is a somewhat similar concept.
That is true. So the question for those who, if you can't hear it online, is how do labels differ from properties? So labels are an optimized indexed way of scanning to a particular subset. So you actually could do it either way. You could have nodes with no label at all, and then you could have a property that says, let's call it type, right? And then say a node with type equals person, all right? When we get to how the Cypher query language works, labels are a lot more intuitive to use in terms of structuring your domain, and they're also more performant underlying in terms of how the database is implemented. But you could do it either way. Like if you came onto our community forums and asked that question, we would probably say you can do it both ways, but please use labels for lots of reasons.
Thanks.
Okay. One of the really cool things about this graph model that we're talking about is a property that we would call whiteboard friendliness. When our field engineers go out and work with customers, frequently the customers have not been exposed to graphs before, and they don't really know how to approach working with graphs and modeling their data. So just in a very human, open way, we get a whiteboard out, we get some markers, and we say, so tell me a little bit about your domain. So you've got customers, and so you draw a little something on the board, and you say, well, they buy products, so let's draw another little circle called product, and then create a link between them. And so you have this elicitation session, if you will, where you're trying to get them to talk about their domain, what's important to them, what the data means, and you draw that out. And so to give you a simple example, if we were talking about movies and actors, you might end up with a whiteboarding session like this. So you got Tom Hanks, who acted in Cloud Atlas. Hugo Weaving was also in Cloud Atlas. But, I don't know if you guys like The Matrix. At Neo4j, we love The Matrix. Okay? It's in the name, people. All right? We love The Matrix. Anyways, so Hugo Weaving was Agent Smith. He was in The Matrix. And then Lana Wachowski happened to direct both of those movies. So you can elicit this information from a user, get this really rough whiteboard sketch going, right? And we're like, wow, look at that. That's a graph. We got a node called Tom Hanks who acted in Cloud Atlas, and so on and so forth. So that's how simple the translation was. We literally just applied this on top of it. Then what we're going to do is we're going to slap some labels, and we're going to propertyify, if you will. What do we care about? People. What do we care about these movies, right? So a person who is an actor has a name and maybe a birth date. When we say that they acted in a movie, it's probably important to know what role they played, so we'll give that a role property. Cloud Atlas was definitely a movie, and we're going to want to track what year it was released in, and so on and so forth. So when we say whiteboard friendliness, this is what we're talking about. Go from I understand my domain inside of my own head elicitation session to a rough model that we can query really quickly. All right? Now, I don't know about you. I worked with relational databases for years and years and years, and it's very easy to get bogged down in these conversations of should we be third normal form or not, and what the data is and how we think of it often get very radically separated from one another. Okay, so this is a screenshot of what the result of this is going to look like as concrete data inside of Neo4j. When we get to the demo, you'll get to see these springy, cool graphs moving around. So we've talked a lot about graphs, the property graph data model. So that brings us to Neo4j itself. Hopefully, at this point in the presentation, it's not going to come as a big shock or surprise, but Neo4j is a graph database. A couple of properties about Neo4j. We support strong ACID transactions, so we are not an eventually consistent database. You get strong ACID guarantees. It's very, very fast, and I'm not going to ask you to accept that as like a marketing claim. We're going to talk about index-free adjacency, and I'll be able to tell you in terms of data structure why that is. So we can get 2 to 4 million operations per second per core. It comes with both binary and HTTP protocols that have a lot of different language-supported drivers. We'll cover that. We have a clustering approach that provides for high availability, so you can have multi-node clusters, and you can survive the failure of multiple nodes in your cluster and still retain those strong ACID guarantees and stay in operation, and no size limit.
Question.
Yes?
You said this is available in Azure Marketplace. I was just looking it up. So it's available as your own VM that you can run, or is it available, or do you take this and put it into your VM as a database? And so how do you actually use it?
Is it us, or is it like service? Are you offering it as a service, or you offering it like here's, essentially you need to install it and you need to take care of it yourself?
It is not available as a managed service at this time. That's something that we're actively working on. So it's provided as a VM-based deploy. So yes, you take care of the VMs once it is launched. Okay? But you can, of course, create your own VM and then install it much as you would any other software package. But I wouldn't recommend doing that. We provide it on the Azure Marketplace. It's way faster to just launch the version that we offer that's already configured nicely and so on and so forth.
Okay, great.
Okay. So it's a native graph database. It's schema-free. Schema-free is a little bit misleading. It's kind of schema optional. We have many schema constructs, but they're not required that you use them. Let's see. It gives you a really nice developer workbench that you'll see. And one of our superpowers relative to other graph databases is the Cypher query language. We're going to talk a lot about that and why that is so important. Let's talk about it right now. Graph querying.
Can I ask
Yes.
a couple of questions?
Sure.
About Neo4j. How does it compare with the graph capability of SQL Server that was recently introduced and with Cosmos DB, which also supports graph using different query language? I believe it's Gremlin.
I have a very specific answer for that, but it's coming a little bit later. Can I park that question and return to it?
Okay.
Okay, because that kind of gets into, I mean, the really short answer is if you have a graph abstraction, you can kind of sort of do graphs either way. But the underlying implementation matters a lot in terms of your performance and scalability expectations. And I hope to talk a little bit about how that's implemented under the covers. And then when we talk about how graphs work on top of SQL Server, you'd see some clear differences. Okay? So I don't let me dodge the question. Okay? It's just that, like, if we haven't talked about Cypher, I'm going to give too much information too soon.
Okay.
All right? So Cypher is a pattern matching query language made for graphs. Now, I'm a big database geek. Neo4j is not the first database that I've ever worked with. I kind of love them all for different reasons. Okay? And one of the things that I'm completely unreasonable about at this point in my career is I have to have a declarative query language. I do not want to write code that goes and tells the database how to fetch data. I want a declarative language where I express what I want, and then it's the database's job to go figure out what's the best query execution plan to go do that. Now, if you guys have been using SQL forever, and most people have, you're used to this, all right? You just express what you want, and you don't think about which index gets used first or anything like that. Like, this is an extremely powerful thing, and yet some of the newer NoSQL databases have trained us to go do with less than that, right? And so this is a point where I'm going to be unreasonable. You need a declarative query language if you're going to work on a serious database, and Cypher is that for graphs. Did you have a question?
Yeah, actually, one of the string online just let you know there's a little delay. So this question may be a little bit delayed, but someone was asking, does Neo4j support graph streams?
I would ask the questioner to clarify that. So yes, in the sense that you can ask a query and the result can be a stream of things that you process as it comes back. But I'm not sure if I'm getting to what the questioner is asking. So Cypher is a pattern matching query language made for graphs. It's declarative. Hopefully I've already convinced you that that's a really good thing. It's expressive, and it's focused on pattern matching. Now, if you remember the whiteboard friendliness point, you can probably follow why pattern matching is important. We want to be able to write a query fluently as we think about how the data is structured. So here's a pattern in our graph model. We've got Dan loves Anne, 2 nodes in a relationship. What does that look like in Cypher? It looks like this. A person named Dan loves a person named Anne. I mean, you can read it from left to right, and it almost looks like the actual pattern in the graph. So this :person is how we tell Cypher we're talking about a label. The brackets is how we talk about that property map that we wanted, right? So name equals Dan, loves person Anne, labels and properties. You'll notice that in the round brackets, parentheses, if you're American, are nodes. So when we ask to create a pattern, we can do the same thing with labels, properties, and relationships. So we can create an entire pattern in the database just by that, by like visually describing it and just saying, hey, go make me one of those. We can also match, and we can create these variables. Okay? So a person named Dan loves whom? Return whom. That's, you guys probably don't have a whole lot of Cypher experience, but everybody ought to be able to tell me what that query does, right? All right, great. So we've got 2 nodes, and in this second case, we're creating a match to a variable on the second node, and then we're just returning what that variable should be bound to as a result of what's in the database. So let's look at a social recommendation query example. This is our VP of product. His name is Philip. And here's one of our product managers named Andreas. And this guy, he's amazing. I hope you run into him someday. His name is Michael Hunger. So these guys are friends, and they like certain sushi restaurants. So iSushi serves sushi. Sushizam serves sushi. They're both located in New York. Philip Rathley here finds himself searching for sushi restaurants in New York that my friends like. Frequently, a lot of these social recommendation type questions can be phrased as a graph path. And so how you would answer that in Cypher would look like this. So I'm looking for a person who is a friend of somebody else. That friend likes a restaurant. That restaurant is located in a certain location, and it serves a certain type of cuisine. And the variable bindings that our user has given us is that the person's name is Philip, we're talking about New York, and he's interested in sushi. And so these graph patterns with a couple of variables thrown in get used to drive the social recommendation.
What is the difference between a lowercase person and the capital P person?
Okay, so before the colon is the name of a variable that's being bound. After the colon is the label. Okay? Yeah, so the label on the node, right?
There's no schema, right? So when you say the label of node, what does it mean exactly?
So we talked a little bit earlier about how nodes can have a label, and that's sort of like the semantic category of information it is. So this node represents a person. And this person, whoever wrote the query, chose the variable name person. So it looks a little bit misleading, right? But the lowercase person is the name of a variable, and then the uppercase P is the label. Basically what we're saying is whatever gets matched to this variable must be labeled person. Does that make sense?
And if a node has multiple labels,
then it will match.
It will match too.
It will match too. If it's labeled both person and enemy, it's still a person.
Where do you put name, location, cuisine? So are those properties? What is that?
Yes, they're properties.
Okay, so where do you define those actually?
So when the data was created, this node got created with that property. And so basically this is placing a constraint that the only persons who can match are those having a name property whose value is Philip. Okay?
So I've got a clarification.
Sure.
If you want to jump back. So going back to the does it support streams?
Uh-huh.
They're asking basically streams of small graphs like syntactic structure of sentences, or this graph could come from Twitter, for instance, and a use case would be extracting significant patterns in real time.
Ooh, okay. Yeah. There's so many ways I could go with that question. Google Neo4j and NLP. I wrote this long Medium article about natural language processing with Neo4j, and that one link, which I can't go into that for time reasons right now, has a lot of information on this topic. On the streaming thing, the person can also Google Neo4j streams, and there's a Kafka integration that talks about producing transactions as a stream or consuming streams from Kafka and putting them into a graph. And so hopefully that's going to help without going too deep.
Okay, cool. Thanks.
Okay, so in our earlier example, we had a really tiny graph. Now imagine this happens in a super massive graph and you have hundreds and thousands of friends. Basically, what these queries are doing is they're finding the best starting points and then they're traversing through the graph from those starting points. Declarative query for graphs. Sometimes our developer relations people find these things that people said on Twitter, and that's like particularly emblematic. Like we couldn't have said it better if we had had our own marketing people do it. So they cap these things and then keep them. What I learned in Neo4j training today is that you draw ASCII art to code. So how true is that? Nodes are drawn with parentheses. Relationships are drawn with arrows, with additional details in brackets. Patterns, you connect nodes and relationships with hyphens and optionally specifying direction. Now you'll notice this is a relationship going one way. This is the same going the opposite way. You can traverse it undirected. This is saying, either way, right? It'll match either way. But the components of a Cypher query basically look a lot like SQL, just with adaptations. So match and return are keywords. M is a variable, movie is a node label. We actually covered that just a moment ago about how to tell what's the variable and what is the type of information you're trying to match. In this particular query, P, R, and M are variables. Notice that we can bind relationships too, and we can return them as first-class types. And we can specify that a relationship we want to traverse must be the acted-in relationship. So, yeah, this is pretty straightforward. The only addition here is that sometimes what we want to match is not the node and not the relationship, but the path itself. So in this case, what we're doing is we're drawing a pattern, we're assigning that to a path, and then we're returning the path. We have a host of built-in functions that allow you to manipulate paths. So for example, you can ask how long it is, you can ask which node is in the third position, so on and so forth. So graph versus tabular results. If you do match M movie, return M, okay, basically what you're going to get back is a node. If you do return m.title, m.released, you're going to get a data square. And it's going to be a table, just like any other, right? Properties get accessed by saying variable.property_name. So in this way, you can return graph components, paths, relationships, nodes, or you can just return tables of information, much as you would with SQL. Not terribly interesting, just moving quickly through this. Cypher keywords are always case insensitive, and node labels, relationship types, and property keys are always case sensitive. Match on the right with funky capitalization is fine, and acted in is always strictly all uppercase with an underscore in between, no exceptions. So aggregates in Cypher, they're a little bit different. We never need to specify a grouping key, and so in SQL you have this group by concept that does not exist in Cypher. We always group by any non-aggregate keys in the return statement. So if, for example, you did this, give me all of the movies that this person acted in, you're going to aggregate that by the individual actor's name. Notice there's no group by statement here. That's a thing we want to pull out. This is something that often trips people coming from SQL going to Cypher. Is they're like, how do I do group by? And the answer is you don't. There's a bunch of different aggregate functions. At the very back of the presentation at the end, I'm going to give a lot of different links and resources. There's a thing out there called the Cypher ref card. If you Google Cypher ref card, it is kind of like the one-page cheat sheet of everything you could possibly want to know about Cypher. It's the 90% solution to most of my problems when I'm working with Cypher. Let's talk a little bit about constraints and indexes. Now, Neo4j doesn't have formal schemas as such, but we do support a lot of different kinds of constraints and indexes. We can create unique constraints. Basically, these allow really fast lookup of nodes that match by properties. And this is how you would do that in fairly straightforward English. Create constraint on label. Assert that a certain property is unique. And so in much the same way as you create a primary key, this is how you would do roughly the equivalent in Cypher. Oh, by the way, that's unique with respect to this label. It's not globally unique in the database. It's, so constraints are always bound to a certain label. So there are three kinds of unique constraints. You have the unique node property constraint. You have the node property existence constraint. So for example, if we want to create a person, we want to always ensure for data quality that they always have a name. Can't ever have a person without a name. And we can create relationship property existence constraints saying, like for example, don't create a company record in our database unless you know who the CEO is. So company is controlled by CEO. Okay, company can't exist without a CEO. So in general, indexes allow fast lookup of nodes just as they do in other databases. You can create an index like this. This places no particular constraint on the values, but it drastically increases the selectivity of queries when they execute. And this is how in declarative languages you hint to the database how it's going to build a plan and how it's going to execute a query efficiently. These predicates all use indexes. So when you create those, inside of Neo4j2, we have a way of backing indexes differently. So you can create Index is backed by Lucene or backed by our native implementation, and there are some other options as well. So you have some flexibility with your data types. If you know more about your data type, you can choose a non-standard index type and improve performance. So indexes are only used for finding the starting points for queries, and you'll find this is really a pattern with graph query overall, is fundamentally we're not scanning through millions and billions of records and trying to filter that, but rather what we're doing is we're trying to identify starting points and then traverse out from that. When we talk about index-free adjacency, the operation of traversing a relationship is fundamentally very cheap in Neo4j, very fast. And so that's why you're going to do it this way. We use index scans to look up rows. In Relational, you use those index scans to look up the rows and join. And in Graph, you use them just to find the starting points, and then you traverse. OK, so one last tricky thing about Cypher I want to talk a little bit about before we move on is merge. Merge is, how many folks are familiar with upsert? You know what upsert's about? This is kind of like the equivalent of upsert. OK. So when you merge, it is create if it does not exist. So when we say merge p person name Tom Hanks Oscar true, so if there is not a person node with name Tom Hanks and Oscar true in the graph, but there is somebody whose name is Tom Hanks, what do you think is going to happen here? It's going to create the node. If you took off the Oscar as true, it's going to match entirely on what is in the merge statement. If that exists, it does nothing. If it does not exist in its entirety, then it gets created as such. So one of the biggest stumbling points with Cypher is somebody runs a query like this, and they already had a Tom Hanks, and now they have two Tom Hankses. All right? So quickly, some write queries. You know, create, that's pretty much as straightforward as it gets, right? OK. We're going to create Mystic River, 2003. All right, what we can also do is if we wanted to modify that, but we didn't actually want to create the record, we can match it and then set its tagline to be this famous quote from the movie. I think I've got some coworkers who are real nuts for Mystic River. I was lobbying for a Matrix example, but they went with Mystic River. OK.
You had to be there.
Absolutely. OK. So what if we wanted to create a relationship between two existing nodes? Well, we would match them both. We've got Kevin Bacon, we've got Mystic River, and then we would simply create a relationship between them. Now, you'll notice on either end of that relationship, we're using a variable, which is already bound to something. So we're not saying create a node. OK, that results in only the creation of the relationship. And what we return from that is PRM, the whole, all three components. So we've got the merge person Tom Hanks example with just the name versus with Oscar equals true. Suppose you wanted to make sure Tom Hanks got an Oscar, but you didn't know whether he already existed or not. Then what you would do is you would merge just Tom Hanks, guaranteeing that it would not create one if he already exists. And then you would set P Oscar equals true. This would be the way that you can get only the Tom Hanks and also modify him at the same time. Yes?
In this scenario, if there was a record with Tom Hanks and Oscar equals true already in the database, would this create a second Tom Hanks node?
No, it would not. This would, in the merge, it would not create it because there is one already existing. That one existing would be bound to the variable P. And then in the next clause, the P's Oscar property would be set to the value true. So this is shown specifically to illustrate the difference in merge semantics between create. The bottom line is that merge checks everything that you give it. And so you want to merge only on your key values, if that makes sense. And then set anything else. And in this way, you can do what you want to do.
What was the difference between this merge and the way you wrote it earlier?
So, okay, that's what I'm trying to illustrate. So this is the first merge, and this is the second merge. Okay, in this merge, what we're telling Cypher is, go find me a person who has named Tom Hanks and who has Oscar true. If such a thing does not exist, create it. Okay? That'll work. That'll always work. But if there is just a Tom Hanks who does not have an Oscar property, okay, then you'll end up with 2 Tom Hanks in your database. Make sense?
Even with merge?
Even with merge. Because you specified that you only were looking for a Tom Hanks where Oscar is true. If you do it this way, it will look to see if there's any Tom Hanks, irrespective of whether or not he has an Oscar property. Okay? It'll find that Tom Hanks, and then it'll ensure that whoever that guy is, he's got an Oscar. Make sense? In this scenario, you will end up with 1 Tom Hanks. Okay? I point this out because this is a common stumbling block about merge semantics that is usually pretty easy to explain, but folks need to know how that works. So merge also has these other 2 options. You can do onCreate and onMatch. So for example, if it mattered to you whether he was new or not, then you could say onCreate, give him a timestamp of when he was created, and specify that, as of his time of creation, he's never been updated. But if you actually matched him, okay, then you don't want to update the created timestamp because you didn't just create him just now, but instead you want to increment his updated counter. Okay? And in this way you can, the Cypher planner will tell you whether or not it actually gave you something that already existed or whether it created something as a result of the merge. Okay. Before we go into data import, any other broad questions about Cypher? Yes.
So can you create relationships and nodes at the same time?
Absolutely. If you say create, and then you give it a pattern that has any number of nodes and relationships, it's going to create all of them at the same time in the same transactions. Yeah. Yes.
So you made an example of saying person love movie, right? You return. So what if, for example, the label for a person, there are multiple, like Tom Hanks, and for movie, the same name of the movie, occurs several times. In this case, what do you return?
Suppose there were, say, 3 Tom Hankses or 3 Mystic Rivers.
Yeah, and they all love 3 movie with the same name.
Yeah. In this case, your variable would be bound to 3 different instances. And then if, for example, you said set the property on this variable, you'd be setting it across all 3.
Not merge. When you do query, just return what result you return.
Same thing. If you just did match person named Tom Hanks, and there were actually 3, then that variable would be bound to 3 different nodes. And so if in the next clause you then set the property Oscar equals true, it's going to get set on all 3.
So, okay, so I see. So if for example, person love movie names show up 7 times, and the person name, there are, say, 5 nodes, and then there will be a 5 times 7 results returned, because each pair of them will form this love relationship.
Mm-hmm.
Right?
Yes, that's possible depending on what the data in your graph is. But we need to get to a more particular example there. So it's like what you're asking about is a Cartesian product.
Yes, because there are many ways, because you're talking about graph. When you talk about graph, there are many ways to organize results.
Yeah.
So I'm asking, which way do you choose to organize the results?
I'm not trying to dodge the question, but it just depends on what you want out of the database, right? So
That's
you can
exactly the problem. You need to infer what I want, right? When I say person love something, what do I really want?
Oh, there's no inference that's happening, right? The database is going to give you exactly what you ask for, but you need some practice with Cypher to specify precisely what you're looking for. So usually that's where you kind of go back to what I said earlier, which is you identify the starting points in your graph, like person named Tom Hanks, and then you traverse out from that. It's possible to create Cartesian products using Cypher, but you don't usually want to do that.
What I'm trying to say is you can't really avoid ambiguity in the data. For example, the same label will always show up multiple times. No matter it's person or movie, right? So in this case, whether it's a precise language, well-defined language or not, you need to deal with this situation, right?
What I can say is I've worked with Cypher for a couple of years, and I have not run into a situation where I could not avoid ambiguity. I would welcome a concrete example of that, and then maybe we could work through how to reformulate the query. Now, it is possible to express ambiguous queries, but I believe that that's true of most query languages. And I think we would really focus on tuning the data model and tuning the query to get to specifics. I'm not saying it's not possible. I'm just saying if that's difficult, don't do it that way, Yes?
I think it's going back to your previous examples of Tom Hanger again, at the delay from the other side. I think you may have covered this, but it said, what if you get more than one match from Tom Hanks? Not that it didn't exist, that you got more than one.
So in this particular, is the question about match or merge? Or did they not specify?
What would happen as an example if you actually came back with more than one match?
Right. Okay, so if you use the match keyword, then the variable gets bound to as many of them as there are. If you use the merge keyword, you're basically saying get or create. Okay? And so if you say get or create, then it's going to end up being 1.
So if it actually found multiple, so it shouldn't find multiple examples of Tom Hanks. It should be unique.
Right.
Okay, that's implied there. Okay.
Yeah.
I think I missed that part.
Yes.
And so here the name is effectively used as the identity attribute of the
Yes.
of the node. So
Yes.
is there a way to enforce uniqueness of identity attributes?
Yes, absolutely. We covered that a bit earlier. That's in the unique. If I can back up to unique node property constraints. So there you would say, you want to create a. Where is it? Create constraint on person assert label.name is unique, and then in this way, if you attempted to insert a second Tom Hanks, it would fail. Okay, so I mean, it's really the same as you do it in many other databases there. All right, let's see. Moving forward. Okay. So, data import. There are so many different options of loading data into Neo4j. I can't really cover them all, so we chose to focus on one of the most common, one of the simplest that people use the most frequently, called load CSV. It lets you take a CSV file from HTTP or file URL, gives you a stream of records, and then basically pipes those stream of records into a subsequent Cypher query, which you can use to create and update graph structures. It gives you transactional operations, so whenever you do load CSV, it's happening in the context of a big transaction. You can transform and convert stuff as you go, and it's a primary way that when people are getting started, they insert data into Neo4j. It works up to, say, 10 million or so nodes and relationships. Because it's transactionally bound, if you wanted to put, let's say, 20 gigabytes of data into a graph, you wouldn't want the overhead of transactions, and you would use a separate tool called Neo4j import. But for simplicity, we want to talk about load CSV as a simple way to get started. Let's take an example. Sticking with the movies theme, we have a simple movies CSV file. Hopefully this is pretty self-explanatory. Titles, release, and taglines. We have a people CSV file that just gives us a name and when they were born. We have some actors. You'll notice movies, roles, and persons. So this is like implicitly telling us about an edge in our graph, right, or a relationship, that this person was in this movie. And then you have some directors. So recalling our data model, a person acts in a movie. A person can also direct a movie, because remember, they can be an actor or a director. So for every record in the file, we want to either create a node for a person or a movie. We want to find a start and end node, and then create a relationship between them. So we covered those in the basic sections earlier about how that works. And that's the creating of the relationship at the bottom. So how do we actually read the CSV with Cypher? Using periodic commit basically says batch this up into smaller transactions, so we don't pull in 100 megabytes and then do all of it all at once. Load CSV is pretty straightforward. With headers tells us that the first line of that CSV will give us metadata. From URL, pretty straightforward. We're going to call whatever that stream of records coming back is. We're going to call those rows. And we're going to specify that it's semicolon delimited. It's not comma delimited data. And then that big Cypher thing that I showed you on the previous slide where we're doing all that match and create comes later. And so basically now this variable row is bound, and we can create graph patterns with the content of row. Row will have, if it's the movie CSV file, row will have a title attribute that we can use. Yes?
Another query, sort of bouncing back again. So someone's asking, is there equivalent of a foreign key in Neo4j?
No, there is not. Because so that's a fantastic question. A foreign key in a relational database is a key to somebody else's table, and we put that so that we can do a join. Okay? There are no joins in Neo4j. There's only relationship traversal, and so foreign keys have no purpose. Okay? If I saw a person writing a Cypher query where they were putting a foreign key on a node, and then they were trying to match a bunch of other nodes where its ID was equal to this foreign key that they had on this other node, oh man, that would be a person who's working really hard to, that's a person who's really trying to defeat the model so that they can work too hard. So, but the short answer is no. There's really no foreign key in Neo4j. Related to this load CSV stuff, so in our browser we have this cool function where you can type in :play and then give it a URL, and it'll step you through a nice guide on how to use some of these features. So this is how to go through a mini class on importing data in Cypher. And it's going to step you through the same example that I showed, but it's going to make it interactive and executable for you in the browser. Developing apps. So we have APIs for most of the popular languages. When you talk to a database over the wire, you're using a binary protocol we call Bolt. We support Go, Java, Python, JavaScript, and a number of others. We also have community support for a bunch of other languages, all kinds of different things. There is a Cypher transactional HTTP endpoint, so you can talk to Neo4j over HTTP. We generally recommend that people use Bolt, much as you would use JDBC for a relational database. There's a link to language guides where you can get really simple, just bootstrap me, get me started quickly with Python type code examples. We have a native Java API as well, where you can actually launch Neo4j in memory. And you can use the Java API to define user-defined procedures and access the core API. So the way that you extend Neo4j itself is typically in Java. Neo4j is written in Java. And you can extend the Cypher language by writing your own functions and procedures, much as you can in other databases. Bolt, high performance. It's versioned. It's based on Packstream, supports TLS, and it also does a lot of connection pooling type stuff. So if you're talking to a Neo4j cluster, you would like to talk to just the cluster and not worry about whether you're talking to node A or node B, and that is called Bolt plus routing. And so there's a way that you can set your client app up to use a Bolt plus routing driver to a cluster, and it'll worry about routing the query to the right server automatically for you. So you just ask a question, get an answer, forget the cluster topology. You can extend Cypher with user-defined procedures. We mostly don't recommend people do this until they've exhausted the other options with Cypher. So you can get really far by reformulating your Cypher query or by putting the right indexes in place. Sometimes you need to access some third-party API, or you need to do something extremely performance sensitive, and you can write your own function or procedure to do that and then call that from Cypher. That just gets done with these Java annotations. They're just Java classes that are annotated a certain way. You compile this, you get a jar file, you drop it into the plugins directory, and you're pretty much done, and your server has a new extension. We'll talk a little bit about the migration of relational to graph, because this is a really big topic for us because most folks are used to thinking in terms of relations. Relational, it tends to be simple until it gets complicated. You end up with all of these different joins, and how many folks here have written one of those gigantic, monster, ugly SQL queries where you're joining like 8, 9, 10 tables? Yeah? Yeah. So, relational, now consider the relationships themselves. The way we think about the mapping between these two ideas is, okay, the naive approach. Before you optimize anything, basically think about all your tables and think about the table name. Turn that into a label and make the table a set of nodes. Foreign keys become relationships. That's actually apropos to the question earlier. So whenever you see a primary foreign key linkage, you need to be thinking, in my model, there's a relationship there. Link tables that are used in relational to resolve many-to-many mappings are basically just relationships with extra properties, typically. And then you throw out all of the primary and foreign keys that you do not need. So sometimes you need a primary key to look up an item by its identity, but you never need foreign keys, and so you're storing a lot less data to begin with. Yes?
Is there a good approach to determine whether the data or the problem is suitable more for a relational database or for a graph database, or maybe for a NoSQL database?
Yes. We're getting to your section. Okay? So I can't defer that much longer. We're almost there. Okay? So we know how to query a relational database. We just use SQL, and so we do these joins. Most people are familiar with joins. How do we query a graph? What we do is we traverse. We've kind of covered this. So this is starting to get into when do you use one versus when do you use the other. Okay, so RDBMSs, it turns out that they actually don't handle relationships that well because they can't model or store them without complexity. And what I mean by that is they're introducing artificial extra features like foreign keys, where you are basically propping up the formalism in order to support this thing that you need to do. Okay? The performance degrades with the number and level of relationships and database size, and we can reason about this straightforwardly in that joins are computed at query runtime. Okay? So it's not that this data is pre-joined, but I have to scan table A, scan table B, match things up in memory. And now granted, 30 years of database research has gone into making that super fast, but you still have to compute it every single time. Okay? Query complexity grows with the need for more joins, and as you add new kinds of data and relationships, this is where you get into the kind of NoSQL thing where SQL being fundamentally schema bound is good in the data integrity sense, and it's bad in the evolvability and agility sense because it tends to be inflexible. It's not terribly easy to define a new relationship on the fly and then rewire your graph. Okay? So one of the things we would say is when data relationships are valuable in real time, traditional databases aren't the best choice. And the reason for that is that you're going to be recomputing these joins every single time. And you're going to be doing typically a lot more scans of a lot more data than is strictly necessary. We can also, this gets to when would you use a graph and not relational. Suppose your question was find all reports and how many people they manage up to 3 levels down. Okay, so if I could give you one slide that got me into graph databases, this would probably be it. I had this data lineage problem where I had a directed acyclic graph of data and the things used to derive that. And the question that I wanted to ask was, give me all reports that were derived from information sourced by the Air Force. Don't care if it's 2 hops back, or if it's 5 hops back, or if it's 15. Okay? And oh man, I spent a week and a half becoming a SQL paladin, learning how to write recursive SQL, using stored procedures, optimizing the hell out of it, not getting very far with it. And so basically, I went up the mountain and I consulted with the SQL gods and I got the absolute best advice. All right? And in the end, it still was terrible. Okay? So one of our field engineers, I think they took this. This is an example from a previous customer who ended up coming to the dark side of graphs. I don't know. Anyway. Somebody actually wrote this query. Like, I wish I could zoom in. I mean, I don't want to waste you guys' time by reading this thing to you, but it's a real query. Okay? And there it is in SQL, and there it is in Cypher. Now, the magic here in Cypher is that we can specify a variable number of relationship hops that we want to traverse. Okay? Earlier on, I said that traversing a relationship is fundamentally cheap and very performant in Neo4j because of the way it's set up, and we're about to get to how that works. But here, one line of Cypher with some simple constraints and a return clause gets rid of this much SQL. Why? Because the question and the data is fundamentally graphy. So when you take a fundamentally graphy problem domain and you put it into tables, typically pane results. Now, if you had a fundamentally table-based problem where you said, I have an entry, I just have a customer list of 300 million customers, and all I ever want to do is pull out which ones are in this particular zip code. Relational has been optimized for 30 years to do that well. And I'm not going to try to convince you that that's fundamentally graphy. Okay? But if your problem is fundamentally graphy, I think we can get there. Does it, Y-graph, this is basically about modeling your data naturally, driving the graph model from the domain and from the use cases rather than from your college textbooks that tell you how you need to have it in third normal form in order to reduce redundancy. Whenever you need to use relationship information in real time, and whenever you need this flexibility to add relationships on the fly, you're probably in the graph sweet spot. So relationships are a first-class citizen, and what we mean by that is the entire database is focused around relationships and traversing those, right? So it's not something that you tack on with scans and with foreign keys and with primary keys. It's just baked in. You know, an interesting way that I've heard Neo4j described is imagine if your database had all of its joins pre-materialized, like they had been pre-computed once, okay? Then you're most of the way to a graph database. We have query and data locality. Part of the way that we can be faster is that we identify the starting points and move out from them rather than doing these massive scans. Only load what's needed, aggregate and project as you go, and then optimize disk and memory model for graphs. So I'm going to get to the index-free adjacency here in a second. If you have a social graph with 1,000 people and you average 50 friends per person, you end up with this densely connected graph. And if you ask, is there a path from Favad to myself in this social graph, but I never want to go deeper than 4 hops, okay? First of all, before we talk about performance, can we agree that that's a really ugly SQL query that's very difficult to write, okay? Let's say we warm up the cache and we eliminate a disk I/O for both databases. These are the observed values, okay? And it makes sense. If you think about how these databases are built and that it is a fundamentally graphy problem, this shouldn't be surprising or a hollow marketing claim. Okay, so this is the secret sauce. This is how it works, and this is why I'm asking you to believe that this is very much a more performant database and it's not just marketing. So inside of the database, we use pointers instead of lookups. And so when you have a relationship, it has a pointer on either end to the place in memory you need to go to find that node. Okay? So when you traverse a relationship, it does not scan all of the nodes and figure out what's connected. All right? Second is we have fixed size records, and if you know much about disk I/O, that allows us to rip through a whole lot very quickly and to be able to do offset jumps and index seeks extremely efficiently. Joins on creation. This is what I meant by pre-materializing your join. Okay? The relational database is computing it every single time on the fly. We computed it once when you wrote the data and then never again. So there's fundamentally a computational cost that we don't have to pay every time you traverse the edge. And essentially the secret sauce is that you just spin through that data structure over and over and over again. And that is why traversing relationships is cheap, because it's pointer dereferencing in the end. So if we, this whole concept, the secret sauce, so to speak, online you'll hear us talk about this as index-free adjacency. And so there are articles you can look up on index-free adjacency, but this is really what's meant. And so when we say that the secret sauce is index-free adjacency, this is why we are claiming that relational can't respond sub-second for n-way joins, and that why we claim that relational is not agile is because it requires changes to queries in these new data feeds. Now, back to your question. You were asking about SQL Server, and so hopefully I've given kind of an overview about that. Cosmos is a completely different story because its underlying architecture is different, but you'd kind of see how it structures its data differently as well.
SQL Server recently added graph capability. This is what I was asking about. This was not relational. As far as I understand, graph capability, I'm not sure what services, they added there. I'm not familiar with that part of it, but it's not relational. It's supposed to be like pure graph something. Are you familiar with that?
I'm unfortunately not. I'd love to take a look at it though.
It was added like recently. At least I noticed it like a month ago. I'm not sure.
Oh,
but I had noticed.
2017.
Yeah, I noticed it like
Okay.
a month ago. Maybe it was added. Yeah. So there is something new. When it comes to Cosmos DB, Cosmos DB has a way to look at the data as a graph, and I believe it supports querying as Gremlin. And
Yeah,
this
that's
is what
right.
I wanted to kind of see how Neo4j compares to Cosmos, especially when it comes to performance in the case where nodes would have huge number of relationships.
A large
Like
degree.
huge, I mean
Yeah.
millions relationships.
Yeah, yeah.
Because in the past, when I was trying to use Neo4j, what I learned is that Neo4j does not scale out. Essentially, that you can have a system with a cluster, which is a very 2 or 3 or several beefy machines with lots of memory, and that's all you can have. And if you want to add more data, essentially you will hit a wall.
Okay.
Has something changed from that time? I looked at Neo4j in 2014 or 2013.
So you had like 3 or 4 different things I need to unpack there. So the first is the supernode pattern, which is the idea of a node having hundreds or thousands of connections.
Right.
Okay. It is true that supernodes in general within all graph databases are considered an anti-pattern. Now, most of the time when we run into customers who have this problem, the problem is somewhere in the modeling layer. And so you may wish to make a compromise such that you do not end up with nodes with this crazy degree. Now, sometimes the problem can be reduced in another way. So it matters a lot, for example, whether the node has 200,000 out edges of the same type or whether they are of different types, because that, of course, affects selectivity in the database, right? So in general, I wouldn't recommend a modeling approach that ends you up with hundreds of thousands of links per node, okay? And I think you'll find that common to a lot of the graph databases. Now, on the Gremlin point, so comparatively between Neo4j and Cypher, I've used Cypher and I've also used Gremlin. I was kind of beating on this point about declarative graph query languages earlier, in part because of Gremlin. Gremlin has a very imperative feel to it. It has some declarative features, but in generally, you're telling it how to traverse things. We find this pretty brittle, and so one of the things that you're going to find with Gremlin after you use it for an extensive period of time is that as your data structure changes, you're going to have to go back and rewrite your queries because you told it which way to traverse, and then that structure has changed, right? You're also going to find yourself optimizing the queries for the database. And so you can do graph query with Gremlin. I just find it to be a lot more difficult, sometimes less performant, and less maintainable as well. All right? And there was a third point. I think I'm forgetting.
About scaling out.
About scaling out, right. So the scalability picture is still similar to what you remember. The way that I would describe scalability in Neo4j is that our cluster architecture has a leader and followers. You get vertical scalability for writes, and you get horizontal scalability for reads. Okay? What that means is to guarantee all the ACID properties, you have one leader. Whenever you do a write, it has to be processed through that leader. So you probably can't process more writes than one leader can handle, and so you can scale that leader up. Okay?
But not out.
If you want to scale the graph out, you have the option to add read replicas and additional followers to your cluster. So there's functionally unlimited scalability for read queries out. Okay?
Thank you.
We covered this. So, Ambrose, we're going to get into learning resources, but we want to start some demos and begin with Ambrose, and then I'll show some extra stuff.
All right.
Come on down.
All right. So my name is Ambrose. I'm from the services pentest team of CDG. And today I'm just going to show you like a 10-minute demo of how to import data from CSV into a Neo4j graph, and without using Cypher. So it's a little bit more intuitive, let me quickly show you what problem we deal with. So during the reconnaissance phase of our pen test, we want to, we have lots of data from different tools. So here on the left, we have a direct report to a manager, right? And on the right, we have those aliases mapped to what file they recently opened. So that's from the delve tool output. Okay, so the thing we want to do is pretty much just combine them and see what it looks like in the graph. Okay, so I created a little like helper library console application that will make it a little bit more intuitive for you to import data. So let's take a look at importing the manager data here. So the CSV looks something like this, and in my like little language thing that I made here, pretty much you have to define some metadata about that CSV file. So what nodes do you want to create? So here I'm saying I want to create a manager node from that first column, and then I want to create a report node, the direct report. And then at the bottom here, you specify the relationship, which is manager, which is this manager, the relationship name, which is manager of, and then the second node, which is report. And then here I have the properties. So the ID would be manager, the name is manager, label, which is the type, is MS alias. So I'm just going to run this real quick and show you what that looks like. Wait, hold on, let me make sure that the graph is clear. So this is what it looks like at the end. I'm going to delete it. So here I have Neo4j running locally on my laptop. Okay. So I'm going to run the import manager. Run this. And then you'll see that it's going to take that CSV file and then load it up over here. Okay, so here I have the labels and the names applied to these nodes. Okay, so like later on, we might get some more data about these people, right? So I'm going to import the second set of data, which is the delve data about what file they recently opened, and then we're going to see what that looks like. Here, import delve data down here. So in this case, I made my helper tool merge on the node IDs. So if it sees the user with the same like username, it's going to use that node instead of creating a separate node. So in this case, I'm going to ID the files by the URL, and then the users are just ID'd by username, like they were before. And the relationship is user, and then worked on file. So I'm going to run this import delve data. And here. Okay, I'm going to refresh it now. I'm going to expand it here. So then you can see that, you can see which are the common files that two users have opened, and this is much easier to see than like looking at CSV files, right? And and then I guess you can create whatever Cypher queries you want to traverse this graph if you want. But this solves the initial hurdle of getting some a CSV data into a graph format, right? And one last thing, I wrote the tool here, so you can find aka.ms/csv2graph, and you can download the console application version of this, which it's pretty much the same. You just run it like this. You pass it a JSON config file, and then in that JSON config file, here it looks just something like this. So you pretty much say which folder you want to use, and then CSV files with named direct reports will have this metadata, which is similar to what I showed you before, and then CSV files with delve would have this metadata, and this tells how to create the Neo4j graph. So underneath the hood, I do call Cypher queries, but like if you're just learning this for the first time, it may be easier to just just define the properties like so here. So
you don't need to actually go to CSV, right? You can JSON to Cypher directly.
yeah, so essentially the library I wrote, it doesn't necessarily have to be a CSV. It just has to be just some kind of this just has to be an enumerable, this thing, right? It doesn't have to be CSV. So maybe you can connect to a SQL database or something and then get your objects in a list and then import it that way. So yeah, both the library and the console app are located here. Yeah.
So it's probably the least technical person in this room. That was super impressive and it's super intimidating. So David, why would I choose to do this method for getting a CSV into Neo4j as opposed to the standard built-in query through Cypher?
Let me ask a question before I answer that. So, did you read the files line by line and then use create and merge, or did you take the data from the user and then run load CSV in your code?
No, I didn't run. It doesn't run the load CSV thing.
Okay.
I did a custom. Yeah.
Well, so a really good reason why you would want to not use load CSV would be, for example, if you needed to do something in your programming language that was well supported in your programming language, but it wasn't in Cypher. So I've seen users do stuff, for example, maybe you get some addresses and you want to run them through Google's geocoding API, and what you want to put into your graph is latitude and longitude. Okay, you can't call the geocoding API from Cypher, but you can do that in a C# program. That would be a good reason, right? Another is that you may know more about the form of the data and you need a really high performant insert. So you might choose, for example, like load CSV will say batch 500 records at once. But if you're doing a zillion of these, you might want to batch them in a particular way for performance reasons. But I think that the biggest reason would probably be programming language specific features where you're not really just loading data, but you're transforming or enriching or cleaning or doing something else with it. So like load CSV is a pure Cypher solution, so you can do anything with that you can do with Cypher, but Cypher is not a general purpose programming language. Yeah. It's a graph query language. Yeah. Does that make sense?
That makes perfect sense. So that really gets back to the core question of what problem are you trying to solve, what question you're trying to answer.
Yeah.
Okay.
Well, this being technology, there's always 15 ways, different ways to do the same thing.
Exactly.
Not necessarily wrong.
Yeah.
Do you mind if I ask you, in your learning curve, when you first got started with Neo4j, can you recall anything about it, just for people who are new, that you particularly liked or thought was good, or sticking points where you particularly had problems or didn't understand the concept?
Yeah, I found the querying by relationships really helpful. The fact that you can just I just like the querying, like you had different levels. You can query down 3 levels. That was good. What I didn't like too much is around like creating nodes, because it's kind of awkward. You don't really create nodes much when you're using a Neo4j graph, right? So like every time I need to create something, I kind of had to reference back. So that's kind of why I created this helper tool, so I don't have to remember what the syntax was for creating stuff. So that's yeah, that's the only thing.
I think that's totally fair.
Yeah, it's totally fair. I mean, half of what engineers do for a living is automate away the pains and the problems that they have. So, that's really cool. The other question is, so you have this graph, right? And you can put all this CSV in it. Have you guys looked at any kind of analyses that you might do on top of that? So it sounds like your use case is fundamentally like analysis. If we know all these people in this department are looking at these documents, have you looked into what are the top 3 most influential things that are the most widely read? Or you could say, if you knew who wrote these documents, you could say, internally, who are the top 5 most read authors at Microsoft?
Right. Well, yeah, those are good questions. I haven't really figured out what the exact query is for that, but
well,
yeah.
It sounds like you could do that easily.
Yeah, that would.
Basis
Yeah,
of your data. It'd be
right,
fun to
exactly.
find out who the David Baldacci or Stephen King of Microsoft is, right?
Yeah. Yeah. So yeah, that's
with probably significantly lower numbers.
I don't know. Microsoft's a big company.
Email recipient or email sender. Here's the
So yeah, that's pretty much my demo. You can get it at that URL, and just feel free to reach out to me if you have any issues. So I'll hand it back to you.
Awesome.
Yeah. Thank you.
All right, so I'm going to take you through a couple of different demo-related things. We're going to talk a little bit about tooling and sort of show you how the software actually works. Just before we begin, as I said, this is on the Azure Marketplace, and so when I showed up today, I deployed a 3-node cluster. Here it is. I've got my core node set, got all my Azure resources. I can show you logging into this later and show you how the cluster topology works, but basically anybody can do this. You go to the marketplace right here, and I type in Neo4j, and we get lots of different options. 3.5.1 is the latest, so Neo4j Enterprise is a single node setup where you're going to get one machine, and Causal Cluster is a multi-node cluster setup, and so if you're just looking to play, you do not need 3 VMs to do that. Or 9 or 15. It depends on how you want to scale. But Neo4j Enterprise will do. If you want the high availability guarantees, then you would go for Causal Cluster 3.5.1 right there and launch that. So quickly, I want to show you this tool. This is called Neo4j Desktop. And so inside of Neo4j Desktop, you can create lots of local graphs and have multiple instances of the database running just on your machine if you don't want the cloud setup. So here I've got a Microsoft demo graph, which I'm going to start right now. And inside of Neo4j Desktop, you get these things called graph apps. These little tiles up here at the top are applications that you can run against a Neo4j graph. And so what Ambrose was showing earlier is this application here called Neo4j Browser. And this is kind of like, a lot of the times when users first come to Neo4j, this is their first point of entry. Really, it's just a Cypher command execution shell with some graphic stuff built on top of it. So I saw him execute this query. We're going to do the same thing on mine. You're going to be shocked to learn that I have movie data in my demo set for today. And so I've got this big graph, right? This tool will allow you to, for example, select nodes, and I can, for example, change the colors of all of them. And I can change how they're captioned and make some nodes bigger than others and so on and so forth. It's a force-directed layout. But basically, it is a command shell. You can run queries and then capture CSV directly as a result of this. One thing, if you're playing with this, I would recommend that you check out the play command, :play. It will run in browser guides where you can do learning and examples and tutorials. So for example, a lot of the stuff that I've shown you today, if you do play movies and then hit enter, it will step you through a little guide. We're not going to do this right now, but this is what the guide looks like. It'll tell you how to create this graph, and you'll see these little play buttons. I can click on the play button and it'll automatically insert that. So as I step through the tutorial, I can execute stuff and start to play really quickly. All right, so that is kind of Neo4j Browser. I'm going to keep a picture of my graph up because we might need to compare it when we look at some of this other stuff. We also have this tool called Bloom. Bloom is for exploratory visualization. So whereas browser is kind of for command execution, run Cypher, get a result. See, the trouble with that is that you have to know Cypher and you have to be kind of a data engineering sort. Bloom is a more natural language focused tool with better visualization where you're going to start in a particular point, not execute an analytic query, but you're looking for patterns. You're looking to identify bigger issues. So I can say, for example, person named Tom Hanks. And you'll see that it interprets that as a graph pattern. It thinks what I mean is match a person with the name property Tom Hanks. That is what I mean. Here's Tom. Let's Command E to expand him, and we blow out just his immediate hops. And then we might say, "Ooh, You've Got Mail is not a great movie. Let's skip that one." Let's see, what was a great movie? Joe versus the Volcano. Anybody seen that? That's some knowing laughs back there, all right? So Joe versus the Volcano, it's about a man who gets convinced that he has this fake brain condition and he's going to jump into a... Anyway. I can't go into that, but let's expand Joe versus the Volcano because it's a funny movie. We've got Nathan Lane, John Patrick Stanley, and Meg Ryan who were in that movie. They're all connected to Joe versus the Volcano. And now let's say we want to just... we can then explore further and say, I happen to know that Meg Ryan was also in You've Got Mail. So if I expand Meg Ryan, look at that. Sleepless in Seattle pops up as a movie they were both in, and You've Got Mail. So we can sort of see the commonalities. Let's pick Tom, Meg, and You've Got Mail, and dismiss everybody else, and then refocus. So this kind of GUI is basically meant to do these kinds of exploratory visualizations. A lot of our financial clients, for example, they might have an idea of how fraud is happening within a financial graph, but not really be able to quite nail it. And so you can use this for hypothesis exploration, where you say, I think this is the pattern that's happening. Now let me go look for evidence of that, and then rinse, lather, repeat to build an overall picture of how the network works. As Ambrose said earlier, it's just so much easier to actually see this data as a graph sometimes that it spurs a lot of discovery in that way. So that's kind of a quick overview of Bloom. We also have a graph app here called Halen, which is for monitoring. Let's close this one and do instead our cloud instance. See if we can get that working. Here inside of Neo4j Desktop, I've got this second tile, Azure deploy. That is this deploy that I set up at the very beginning of the meeting. And I'm going to activate this as a remote database, not running on my machine. And I'm going to open my little Halen graph app. And what I'm going to see here is a lot of operational metrics about a multi-node cluster. So along the top, you'll see these 3 IP addresses are the machines that are participating in my cluster. The one with the little star is the leader of the cluster that takes all the writes. And the other 2 are followers. And basically, this is a rather in-depth program. We're not going to go all the way through it, but you can hover here and you can sort of see it's got this green status. Everything's looking good. That's because it's basically not doing anything right now. The cluster is idle. And then we can look at individual machines and, for example, take a look at what the memory or the disk on this machine is doing. What plugins do we have installed, and how is it configured? So, for example, I can type in here, I can see what addresses it is advertising to the broader network. One last thing about Halen is in the Diagnostics tab, you can run diagnostics, and it will gather a lot of information about your cluster and give you recommendations on what looks good, what might be misconfigured, what you might want to look into, and this sort of helps users diagnose some of the most common problems associated with configuring clusters and so on. Okay, so any questions about kind of like the graph app concept? We have an API online so that if you wanted to write simple applications sitting on top of Neo4j, this is a pretty good way to do it. In the end, they're just JavaScript programs, typically with a certain JavaScript stub API injected that allows you to connect to and talk to the graph with a Bolt driver instance. Okay? Yes?
Is the same monitor UI available from the VAP interface?
Yes, it's the same.
Okay.
The only difference here is that it's wrapped inside of a graph app, but it's the same.
All right.
Yes. All right, so that's kind of Neo4j, the nickel tour of Neo4j Desktop. Now let's talk a little bit about the analytics and data science parts. I want to show you a simple, or maybe not so simple query. This is it right here. And it gets to the right browser tab. Okay, so we bootstrapped a whole lot of knowledge into you today about what graphs are, what Cypher is, how all this stuff works. We have this library that comes packaged as a plugin called Neo4j Graph Algorithms, or just call it Graph Algos. For data science groups, data engineering groups, really, really recommend you take a look here, because this is all of the graphy data science stuff here that you're not going to find in other libraries, and that Neo4j makes really easy, that these sorts of things are going to be quite difficult in other systems. So the Graph Algorithms plugin is basically a compilation of a lot of different algorithms across a lot of different use cases. This documentation, I've always thought it's pretty good, because not only does it describe like the syntax of like how you're going to call this or that algorithm, but it also goes into, okay, what is Louvain about, and when would you use this, and if your problem looks like this, then you probably want PageRank instead of something else. Some of the most fun things that I have done working for Neo4j have been interacting with this. So quick story, Neo4j has this data journalism outreach program where we use graph technology, work with journalists who are doing investigations, help them get answers, and then they write up the story and publish it. And when I was brand new to Neo4j, I got to work with NBC News. They were doing coverage of Russian Twitter trolls manipulating elections in the United States. And using the Graph Algorithms package, we loaded a whole lot of Twitter data in that was given to us by the sources that the journalist had cultivated. And we were looking for community issues. That is, what topics were the trolls most frequently talking about? How did they break down across certain demographic lines? And all of that social network data is fundamentally graphy and lent itself well to the algorithms that are in this package. Getting to play with that and doing those kinds of data analyses is really fun. Primarily, I was using at the time the community detection algorithms. We were looking at all of the trolls and saying, if you got rid of all the civilians and you looked at just the people who were involved in this instigating behaviors, who was talking to who was retweeting who? And it turned out that they sort of broke into multiple communities. Prior to the analysis and the publishing that NBC did, the thought had been there's this big group of trolls and they want a particular candidate to win, and that's really the end of the story. And it just wasn't. At least that's not what was in the data. We found that there were a group of trolls who were aligned with right causes, a group of trolls aligned with left causes, and a third group. And that the overall modus operandi, if you will, like what they were trying to do, was more about social division and less about advocating for a particular person in that election. And so that stuff got written about in NBC News. We don't have to go too deep into it, but for data scientist people, I just want you to know that like what went into that reporting was Neo4j and graph algorithms. And this is where you should start if you want to do data analysis with Neo4j. So as a simple example, I did a query for harmonic closeness on my movie graph. This is just computing, whoops. Oh yeah, I didn't start my database. That's going to help. Databases are much more responsive when they're running. So let's take a look at this query. Basically, what we're getting is this metric coming out of the harmonic closeness algorithm. The metric is centrality. I believe with this particular algorithm, the metric in and of itself is not meaningful. So it's not like 2.286 means something, but magnitude and directionality is meaningful. And so this is basically about when you look at the graph, how central is a node or how influential is it in the overall flow of information throughout the graph. And so the way that this query works is that call algo.closeness.harmonic.stream. And so fundamentally when we use the call keyword, we're calling a stored procedure. We're giving it some parameters where we're looking for nodes and acted in relationships. And then basically we yield some data and then basically match nodes in the graph that were yielded out of this harmonic closeness, and then return whether it's a movie or a actor. We order by centrality in descending order to find the most central nodes first, and limit to the top 20. And our buddy Tom Hanks comes out on top. And the reason for that is that when we created this sample data set, it was centered on Tom Hanks, and we tended to add data around him, right? So it's not really surprising in this particular data set that he comes out as very central. Also not surprising is a lot of stuff that he's in shows up being central, because as we expanded out and added to this data set, we tended to tack on co-stars and directors of the movies that he had been in, right? So if, for example, you did this on the entirety of Twitter, you would probably find at the center PewDiePie, Lady Gaga, and all of those, right? Because that's who people are retweeting, that's who's sending out the most content, and that's who's referenced the most often, right? So one thing I can't really do justice in less than a full day class is the depth of how much is in this algorithms stuff. So basically, we kind of group these into families of algos, if you will. So sometimes what you care about is centrality. And that's what I just showed you. Sometimes what you cared about is community detection. So I wish I had I kind of do have a whiteboard. Maybe the cameras will follow me. So sometimes if you have a graph like this, let's say you have a graph like let's say your graph looks like that. Totally made up. But you can sort of see that while there are a bunch of nodes and edges, there are 3 distinct communities in there. And so the family of community detection algorithms are really what they're trying to do is give you this. 1, 2, 3. A lot of these algorithms, as with many machine learning algorithms and other things that you've used, they come with a lot of tweakable and tunable parameters, right? So if you fuzz it enough, hey, it's all one community. And if you make the community stark enough, then you have as many communities as you have nodes here, right? And so as with many other algorithms that you're going to work with, there's some tweaking and tuning according to the domain that you're dealing with and how specific that you want to get. But that's kind of community detection. Now, if you look at this particular graph, if we ask about the centrality of this graph, you don't really get much meaningful out of that because there isn't really any node, with the possible exception of this guy, that's really central in this graph, right? On the other hand, if the pattern that you're looking at is sort of like spoke and hub, like this, and you run centrality, a centrality type approach on that, here we can clearly see, even visually, even without a fancy algorithm, what is the most central node in that graph, right? And so this is where, and I know you guys know this from data analysis, it's just that the technical features offer us all of these cool algorithms that we can run, but then we have to have a whole lot of domain understanding of what our data is so that we can fit this abstract math thing that works, that does something really cool in software, and then fit that to our domain so that we know which algorithm to use and when. That is the real art. That's why we get paid the big bucks, right?
So I have a quick question.
Yes.
Just a use case that we are looking at. We want to actually color certain nodes based on some criteria as we are traversing through the graph. Are there ways and means to do something like that through these APIs, or do we need to do something more custom?
Both depending. So there are pathfinding algorithms. That's a whole class where that might be what you want to do. It depends on how sophisticated your paths are. Sometimes what you want to do is sort of like an iterative algorithm where you find a path and then you set a property on that path. And then you just sort of iterate on that and then you expand it out time and time and time again, expanding out which nodes get this magic property each time. You know what I'm saying?
Yeah.
So it kind of depends on what you want to do. But the pathfinding algorithms are a help for that. But in many cases, because Cypher's kind of good at that out of the box, sometimes the pathfinding algorithms are overkill for that. And you just need some simple Cypher. Can you say a little bit more about what kind of paths do you want to find, and what meaning do they have for you?
Yeah, so essentially, I work on the build-out team. We're building out clusters for Azure.
Oh, okay, cool.
Each of those build-outs have a certain series of jobs that happen. And these jobs have a certain set of dependencies that need to go through as we traverse through that. And so sometimes certain jobs get locked or delayed, then we want to refigure the critical path based on what we're trying to do.
Oh man, so that's a dependency graph. So you're talking about something like an ARM template?
Mm-hmm.
Is that the kind of job?
I mean, ARM is essentially you have a cluster live and you're already doing it. This is still in the initial build-out phase where we are.
So you got some job 1 that triggers job 2, triggers job 3, and then you get to this good place, right?
Yeah.
But job 1 also triggers J4, which triggers J5, which is needed for J3, and J5 is blocked.
Right.
Right.
So we'll color J5 differently. And then
Yeah. So we'll just put a green circle around it and say job 5 is blocked, right? This is very similar to like the network and IT operations use cases, where sometimes what people are doing with graphs here is these are routers and machines, and what they want to ask is, what in this chain, if it fails, will mess up my ability to deliver this? Okay? And so basically what you might want to do is ask a query like start, finish, all right? Okay? And then so you want to enumerate all distinct paths from start to finish.
Right.
And then you want to go through those paths and ask if any component on that path is blocked. Right? That's fairly straightforward to do with Cypher, right? Because we know how to match a path. We know how you can use the distinct keyword to say I want distinct paths. And then you can use functions in Cypher to pull out the nodes. Or you could say match A uses, I'm just making this up as we go, star B, where b.blocked true, and then this will get you p equals return p. I'm just going really fast. Hopefully this is legible. You can say match all paths where I'm going from some starting point to some node. That node is blocked. Give me that path. And then you might further this and say B. Now I'm getting really small. And then say finish. Right? And then that right there would identify the blocker. Right?
So you don't even need one of those. You can just use Cypher straight.
Well, yeah, that's why I was thinking that pathfinding algorithms might be overkills, because you can do this sort of thing.
Great.
Right? And then you could then, for example, color that node by setting a new property on it.
Yeah.
And then if you did that, say, every 30 seconds, then separately scan what are all of my blocked guys, and then have some resolution approach for that. Does that answer your question?
Yeah, it does. Thank you.
Similarity algorithms and preprocessing functions and procedures. Yeah, we're coming up to the end of our time here. I want to make sure that we are respectful of everybody's time and leave some time for Q&A. I've gone through a lot of algorithms and a lot of stuff. Like, I could talk for hours about just this piece, but it gets really deep really fast. And as an intro topic, I just want to leave you with this as a point of exploration. Finally, when you get... This is only going to take a minute or two. When you get lost, where do you go? How do you get help? This is, don't worry about writing these links down or anything like this, because we're going to distribute a copy of the slides, so all this is going to be clickable for you. Everything that I've told you today, you're going to be able to find in written, documented form out here on our developer pages. We have a Graph Academy where you can get self-paced online training. We have a Neo4j certified program where you can go through an exam process to get Neo4j certified, become a professional, and get that sweet, sweet Neo4j swag, right? I mean, this being the tech industry, I know you guys don't have any t-shirts at all, and you're desperately in need of some, and I want you to know that we're here to help, okay? So the 1 hour certification exam covers a lot of the topics that we've covered today and goes into a little bit more depth. We told you earlier about the Cypher ref card. Like, if you only had one link, how do I do something in Neo4j? A single link, don't even want the whole developer manual. This would be it. This is the cheat sheet of everything that you need. Obviously, we have developer documentation, operations manuals for how to run clusters. We have a knowledge base as well. So paying customers get access to a lot of extra articles. We have a very large number of public articles as well as frequently asked questions. They're version specific, so you can find out about how this worked in this older version, whatever you need. Lots of sample applications that you can get, clone, compile, and go. We are very passionate about our user community, and we have regular meetups all over the world. We have a community site, community.neo4j.com, where you can get connected with some of these, and you can meet some of my favorite fellow graph nerds. That's also a great point of entry to just ask a question. We have a fantastic developer relations team that tends to jump on helping people who are out there and wanting to get them started and have a good early experience with graphs. You know, Neo4j grew up in the open source world, so if you want to know, I don't know, maybe you wake up late on a Friday night, you know, when you should be asleep, and you say, how did they implement index-free adjacency? I must go to GitHub and know. You can do that. We have Stack Overflow. You know, one of the early ways I got involved in the community is I answered a zillion questions out there on Stack Overflow. And so a lot of different things that you might want to do have already been covered. Books, man, it's endless, okay? And some colleagues who I have tremendous respect for, we have two people, Mark Needham and Amy Hodler, are in the process of publishing a book on graph algorithms. And so it's going to be a very deep dive on all of the stuff that I can't cover today for time reasons. So when that O'Reilly book comes out, I really highly recommend you pick up a copy because bigger brains than me, I'll tell you that. Anyways, that brings us to Q&A. I want to be here to help you have the smoothest early process and get any of your questions answered, and please don't spare me the hard ones. Ankit.
So in the community, has anyone attempted algorithms which are like used for probabilistic graphical models on Neo4j, like reinforcement learning or mandates, those kind of?
Yes. I am myself not super deep on that. I'm not sure I can answer that really thoroughly. But yes, there's a guy named Andrew Jefferson who has written a couple of posts on this topic, and Octavian AI, I think, is the group that he's working with. And so that's a fairly deep rabbit hole. Like, how does Neo4j connect to deep learning and a lot of those related topics? That's an area that we're increasingly getting into. There's some publishing out there right now, and there's more to come.
And the second question I had was, are there in the plans Neo4j connecting with Power BI?
Power BI. So I think in community open source, there's a number of ways that you can do that right now. There is a JDBC driver where you can write Cypher and expose a table. Okay. There's not a Power BI specific integration that I'm aware of, but we are always, you know, I work in partnerships and so on, and we're always looking to hear about what integrations are most valuable and why. We'd love to talk to you more about that offline. So, man, you guys are troopers. It's like 5 o'clock, and you've been listening to graph stuff for 2 hours. Yes?
Right, so you already mentioned the problem or anti-pattern of supernode.
Uh-huh.
I was wondering what other problems people are typically running into, and what are the early symptoms of those problems?
Ooh, that's a good one. And that's not an easy one either. All right. Man, you took me seriously when I said ask the hard ones. Okay. All right. Anti-nodes are definitely... the supernodes are definitely an anti-pattern. Neo4j does not index relationship types, and relationship properties. And so an anti-pattern that I see is over-reliance on really dense property metadata on the relationships. Okay? So, for example, if the way that you design your model is with very thin nodes and very fat relationships with 20 or 30 properties, and then you want to write a lot of queries that are very selective on relationship properties, this is generally not a good idea. Okay? That's one anti-pattern. Let's see. Super fat nodes where you don't split things out is another anti-pattern. Recall that I've been saying all along, relationships are very cheap to traverse, right? And so let me take a super simple example. Let's say that I have a customer. In a relational database, we're going to give them a name and a state and a city. Let's just keep it that simple. Okay? In relational databases, we tend to think about tables, and so what we do is we pile lots and lots and lots and lots of properties on. And this breeds queries where you're going to be searching for all of the customers who are in the state of Virginia. I'm from Virginia, so I use that as an example. A better way to do this is to take your low-dimensional categorical variables and to break them out into nodes. So, for example, I would not do it this way. I would do it like this. Customer name has state has city. Okay? So an anti-pattern is having lots and lots of really fat nodes and not that many relationships. In this way, you are defeating what the database does well. Okay? And you're falling back on your old relational scan and filter skills. Does that make sense? Was there a second part to your question that I missed, or did I answer it?
Early symptoms.
Early symptoms. Bad query performance, and also the other symptom would be your graph model looks exactly the same as your relational model. That would be a giveaway. So if you have these different affordances and different flexibilities, it ought to look at least a little different. All right, was there a question in the back?
I was just going to say, you would also then define state has city in your graph model?
Yeah, probably so. Actually, yeah. This would help distinguish between Richmond, Virginia and Richmond, California, which I can tell you are very different places. Yes?
So in general, when we're trying to model data as graph, we found that it's kind of awkward to model the time series data in some way. This graphs, what's your recommendation generally? Do you adopt different database models and do a hybrid kind of thing, or?
Yeah. Oh, man, you're really teeing up the softballs for me, okay? So in earlier versions of Neo4j, it used to be that we recommended this time tree approach, and that's probably what you're talking about. Mm-hmm. So in the time tree approach, you would do, just for folks who have not seen the time tree approach, you would have a 2019 node linked to a January node, linked to a, what is today anyway, the 24th day, and then you would link that to a customer call. I don't know, let's say a customer called. And this would be a time tree. And so if you wanted to find all of the calls that happened in January, you would match to the January 2019 and then get all the nodes from there. Neo4j 3.4 introduced a temporal data type. So you can have times and date times as a native data type on a property. And we have optimized indexes for that. And so when the temporal types and temporal indexing came out, we don't do time trees anymore. You just put a date time, you index it, and that's that.
It's like stacking the value on one property with a timestamp or something. Like if you have a history of different values for the same property, so just stack that on the same property with different timestamp.
So if you have a history of values, there's a different pattern for that. So we basically, you turn, if part of the problem of your domain is that you have the customer today, but you want to know every state the customer has ever had in the past, then we're going to basically model the customer as a linked list. And the head of the list is always, so taking our example right here and sketching it out. So you've got this customer call on 1/24/19. And then we'll have a next link, and then we'll have the same one on 1/23/19, and so on and so forth. So when people need to do revisions in graphs, what they do is they basically never modify the node. They create a new one with duplicate data, but whatever they need to change. And the old one gets pushed back on the linked list. Does that make sense? And in this way, you can traverse the chain, and it's like a time machine, right? You can navigate to that node through the query, and then you can go back however many iterations you need until you hit some time point.
I see. So the timestamp you mentioned was basically just a extra attribute on the property, right?
Yes, sir. It's just another property. It's just another property that has the date-time data type.
Okay. All right.
Yes. I'm going to get to your question in just a second. I'm going to just pull that up because why not? So, yeah, so that's what I'm talking about. It's just a property data type. Yes?
Oh, just for clarity. So in that example that you just wrote up, what would the node be under? Would it be another customer call node? Under,
Yeah.
With the different property of a different date?
That's exactly right.
Okay, yeah.
It would be a different property of a different date, but otherwise the same data. And in this way, we would basically be keeping every revision of the node that we had, enabling the time machine aspect in. Call that Git for graphs. You know? Because you can even branch with it. You really can. I've seen people do that. Any other questions? Any online? All right. Thanks a lot, guys. We hit our time. We're over by 2 minutes.
Oh.